In AI modeling for sales forecasting, you can define the training dataset and the output layer, and then use deep neural networks, DNNs, to automatically learn the hidden layers and their representations from the data. The process of determining the architecture and the number of hidden layers and neurons within those layers is one of the strengths of deep learning. Pradeep K. Suri, author and researcher. Here's how it typically works. 1. Input data. You provide historical data as the training dataset, which includes features such as past sales, seasonality, marketing expenses, economic indicators, and any other relevant data that might influence sales. 2. Output layer. You define the output layer, which represents the sales forecast. The number of neurons in the output layer is typically 1 for regression tasks, where you are predicting a continuous value, sales amount, or it can be multiple neurons for classification tasks if you are categorizing sales into specific classes. 3. Hidden layers. The architecture of the hidden layers is determined by the neural network itself during the training process. Deep neural networks can automatically learn and adapt the number of hidden layers and neurons to capture complex patterns and relationships within the data. The depth and width of the network are determined based on the information contained in your training data and the complexity of the problem. For training, you train the deep neural network on your historical sales data. During the training process, the network learns to extract relevant features and relationships from the data by adjusting the weights and biases in the hidden layers. This allows the network to make accurate sales forecasts. The advantage of using deep neural networks for sales forecasting is their ability to model complex, nonlinear relationships in the data. They can capture intricate patterns, seasonal variations, and other factors that might not be easily captured by traditional statistical models. However, it's important to fine-tune the hyperparameters and architecture, and regularly evaluate the model's performance on validation data to ensure it's providing accurate forecasts. The choice of the number of hidden layers, neurons in each layer, and other hyperparameters can be initially based on best practices and then fine-tuned through experimentation to optimize the model's performance for your specific sales forecasting task. To build a sales forecasting model in Python using deep learning techniques, you will typically work with a combination of libraries, including deep learning frameworks, data processing libraries, and visualization tools. Here are some of the commonly used Python libraries for this task. 1. Deep learning frameworks. TensorFlow, developed by Google. TensorFlow is a popular open-source deep learning framework that provides tools and libraries for building and training neural networks. Keras. Keras is a high-level neural networks API that runs on top of TensorFlow, Theano, or Microsoft Cognitive Toolkit. It simplifies the process of building and training deep learning models. 2. Data processing and analysis. Pandas. Pandas is a powerful library for data manipulation and analysis. It is commonly used for loading, cleaning, and pre-processing your sales data. NumPy. NumPy provides support for large, multi-dimensional arrays and matrices. It is essential for mathematical and numerical operations, which are crucial in deep learning. 3. Data visualization. Matplotlib. Matplotlib is a versatile library for creating static, animated, or interactive visualizations. It's useful for visualizing your historical sales data and model performance metrics. Seaborn. Seaborn is built on top of Matplotlib and provides a high-level interface for creating attractive and informative statistical graphics. 4. Machine learning and statistics. Scikit-learn. Scikit-learn is a comprehensive library for machine learning. While you may not need it for deep learning, it can be useful for feature engineering and traditional machine learning models that complement your deep learning approach. 5. Time series analysis, optional. Stats models. If you need to perform time series analysis on your sales data, Stats Models is a library that provides tools for estimating and interpreting models for various types of time series data. 6. Optimization and evaluation. SciPy. SciPy is built on top of NumPy and provides functionality for optimization, interpolation, integration, and other scientific and engineering tasks. Scikit-learn. In addition to machine learning, Scikit-learn offers tools for model evaluation and hyperparameter tuning. 7. Jupyter Notebooks, optional. Jupyter Notebooks are a great tool for interactive development, documentation, and data exploration. They allow you to run Python code in a cell-by-cell fashion, making it easier to experiment with your models. 8. GPU acceleration, optional. If you're working with large datasets or complex models, you may want to use libraries like CuPy and NVIDIA CUDA for GPU acceleration, which can significantly speed up deep learning training. The specific libraries you need will depend on the complexity of your sales forecasting problem and the nature of your data. Typically, you'll start with data pre-processing using Pandas and NumPy, create and train deep learning models with TensorFlow and Keras, and visualize your results using Matplotlib and Seaborn. Additionally, you might use other libraries as needed for specialized tasks such as time series analysis or statistical testing. Important point: hyperparameters in machine learning are parameters that are not learned from the data but are set prior to the training process. These parameters control various aspects of the model's training and architecture and can significantly impact the performance of the model. Unlike the model's weights and biases, which are learned during training, hyperparameters are set by the machine learning engineer or data scientist. Examples of hyperparameters include: important point: hyperparameters in machine learning are parameters that are not learned from the data but are set prior to the training process. These parameters control various aspects of the model's training and architecture and can significantly impact the performance of the model. Unlike the model's weights and biases, which are learned during training, hyperparameters are set by the machine learning engineer or data scientist. Examples of hyperparameters include: learning rate. This hyperparameter controls the step size when adjusting the model's weights during training. A smaller learning rate can make training more stable but slower, while a larger learning rate can lead to faster convergence but might overshoot the optimal weights. Number of hidden layers. The architecture of a neural network, including the number of hidden layers and neurons in each layer, is determined by the model's hyperparameters. Number of neurons in hidden layers. Within each hidden layer, you can specify the number of neurons or units. The choice of this hyperparameter affects the capacity of the model. Activation functions. The choice of activation functions for each layer, such as ReLU, sigmoid, or tan, is a hyperparameter. Different activation functions can affect how the network learns. Batch size. Batch size defines the number of training examples used in each iteration during training. It can affect both the speed and quality of training. Epochs. The number of epochs is a hyperparameter that determines how many times the model goes through the entire training data set. Setting the right number of epochs is crucial to avoid underfitting or overfitting. Regularization parameters. Hyperparameters like L1 and L2 regularization coefficients control the amount of regularization applied to the model. They help prevent overfitting. Dropout rate. Dropout is a regularization technique that involves randomly dropping out a fraction of neurons during each training step. The dropout rate is a hyperparameter that determines the dropout probability. Loss function. The choice of loss function depends on the type of problem you're solving. For example, for regression tasks, you might use mean squared error, while for classification tasks, cross-entropy loss is common. Optimization algorithm. The choice of optimization algorithm, such as SGD, ADAM, or RMSPROP, is a hyperparameter that influences how the model updates its weights during training. Initial weights. The initial weights of the model are usually randomly set, and the choice of the initialization method is a hyperparameter. Architecture parameters. These include hyperparameters like the number of filters and kernel sizes in convolutional neural networks, CNNs, and the number of LSTM units in recurrent neural networks, RNNs. Hyperparameter tuning, often referred to as hyperparameter optimization, is the process of systematically searching for the best set of hyperparameters for a given machine learning task. It involves trying different combinations of hyperparameters, training models, and evaluating their performance to find the configuration that yields the best results. Techniques for hyperparameter tuning include grid search, random search, and more advanced methods like Bayesian optimization and automated machine learning, AutoML, tools. Thank you.